Welcome back to another video. Today we're stepping up from basic algebra equations to explore a highly visual math topic, systems of linear inequalities. Instead of searching for a single intersection point where the two lines meet, we'll be looking at entirely shaded regions on a graph. We're going to break down the foundational rules of boundary lines, look at a neat trick for shading, and learn how to pinpoint the ultimate solution zone where everything overlaps. To start, let's jump right in. To get started, let's look at how an inequality differs from a regular equation. When you have a standard linear equation like y equals 2x minus 1, your solutions are highly restrictive. Only points that sit directly on that line are valid. But notice what happens when you switch the equal sign to a greater than symbol, making it y is greater than 2x minus 1. The line instantly transforms into a dashed boundary, and our solution set suddenly opens up to include an entire half of the graph. Every single coordinate point within the shaded green region makes the inequality mathematically true. Now comes the most important part, the graphing rules. If your problem features a strict inequality, meaning a less than or greater than sign, you will always draw a dashed line. On the flip side, if your inequality is inclusive, featuring a less than or equal to or greater than or equal to sign, you'll draw a solid line. Now, once you've drawn your line, how do you know which side of it to shade? The easiest way is using the test point trick. Let's look at the inequality y is greater than x minus 2, which gives us this blue dashed line. The rule is simple. Pick any coordinate that is clearly off the line, plug it into your inequality, and see if the math holds up. The best point to use is the origin, 0, 0, because the math is very easy. Let's plug in 0 for x and 0 for y. That gives us a statement saying 0 is greater than negative 2. Is that true? Yes, it is. Because the test point gave us a true statement, we shade the entire side of the line that contains the origin. If it had been false, we would have shaded the opposite side. However, that's only when we have one inequality to solve. If you're wondering what happens when we have multiple, let me explain. So what is a system of inequalities? A system just means we are graphing two or more inequalities on the exact same coordinate plane. Imagine graphing our first inequality and shading its region in blue. Then, right on top of it, we graph a second inequality and shade its region downward in yellow. The final solution to the entire system isn't just one side or the other. It is the specific overlapping region where both fields merge together. Any point sitting inside this shared sector satisfies both boundaries simultaneously. Now, let's try a full practice problem together. Say we want to graph the system y is greater than x plus 1 and y is less than or equal to negative x plus 3. For the first inequality, we graph a dashed line with a y-intercept of 1 and a positive slope. Testing the origin 0, 0 gives us 0 is greater than 1, which is false, so we shade the region facing away from the origin. For our second inequality, we graph a solid line starting at a y-intercept of 3 and a negative slope. Testing 0, 0 here gives us 0 is less than or equal to 3, which is true, so we shade the side containing the origin. Notice where the lines cross at the point 1, 2. Because one line is dashed and the other is solid, this exact corner point is technically excluded from the final solution. However, pause the video and think about what would happen if both lines were solid or both lines were dashed. To make things crystal clear, let me help you understand how to find the overlapping region by peeling back the layers to see how the puzzle fits together. Here is our first region shaded in blue, and here is our second region shaded in brown. When we bring both overlays back together on the screen, our eyes can easily lock onto the final target zone. To verify our work, we can also test a point right inside this shared zone. For example, negative 2, 2. If we plug those coordinates back into both of our original inequalities, they both check out perfectly, confirming that we indeed found the right region. Next, let's take a look at our second practice problem. Let's look at a special type of system you'll definitely see on assignments, horizontal and vertical inequalities. We want to graph x is greater than or equal to negative 2 and y is less than 3. Whenever an inequality only has an x, it forms a vertical line. Because it's greater than or equal to, we draw a solid line right at negative 2 and shade everything to the right, where the x values are larger. When an inequality only has y, it forms a horizontal line. For y is less than 3, we draw a dashed horizontal line right at positive 3 and shade everything underneath. The final solution is neatly logged directly in this bottom right quadrant where the purple and green grids cross paths. If you understood this question, let's move on to the real-world example, the fitness app. Believe it or not, your smartphone apps use this exact same math to track your habits. Imagine a fitness app monitoring your weekly goals. Your target goal is to get at least 2 hours of exercise per week, but you also want to make sure you cap it at a maximum of 5 hours to avoid overtraining. We can write this real-world constraint as a compound inequality. 2 is less than or equal to x, which is less than or equal to 5. Visually, the app builds a solid boundary line at 2 and another at 5. The area between them represents a safe zone, where you are actively hitting your fitness goals. Now, let's exercise our minds with a quick challenge. Let's look at a multi-line system. X is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 4. The first two constraints, x is greater than or equal to 0 and y is greater than or equal to 0, are incredibly common in advanced math and economics because they restrict our entire problem to the first quadrant, meaning our values must be positive. Next, we add our diagonal line for x plus y is less than or equal to 4 and shade underneath it. This completely bounds our answers into a neat enclosed triangle known as a feasible region. In advanced math, the most important parts of this region are the vertices or corner points. By finding where our boundary lines intersect, we can pinpoint our three critical corners at 0, 0, 4, 0, and 0, 4. Finally, the summary and conclusion. To sum everything up, always look at your inequality symbols to determine if your boundary line should be dashed or solid. Use the origin as a quick test point to figure out which direction to shade, and remember that the true solution to a system is strictly the region where all the shading overlaps. Once you master the direction of the shading, the rest of the problem is just basic geometry. If this video helped you clear linear inequalities up for you, don't forget to hit that like button and subscribe for more step-by-step math guides. Thanks for watching.